Thank you for inviting me, giving me the opportunity to speak. Hopefully you can also hear me well. All right. So before I really start, I want to give two little bits of something. Okay, I'm not allowed to use those. Okay, all right. I understand. Okay, so let me tell you two things from the start before I really start my talk. So it's like a little pre-teaser. And the first thing I'd like to say is what type of singularities, this is a conference on singularities, so what type of singularities do I care about and what is this about? And roughly speaking, I'm looking at those kind of situations. You all know those things. You can put here a polynomial in the variables u, and then on the other side you have x, y, and sometimes I have also another one, x, y, z. There can be more variables. But that's just the most basic example. I will generalize away from this, and what will happen is that here, so it's like a marriage of a hypersurface singularity, which you can think of as given by this polynomial f, and what the left-hand side is supposed to be more generally is a toric singularity. Okay, so the left-hand side, there will always be a toric singularity, and then a hypersurface singularity. Two very different types of singularities. Toric singularities are typically not normal crossing, and not complete intersection. And that's what I look at. That's what I deal with. It's happening through and through, and I'll try to explain you the global theory about that. Okay, so I can locally write that down. You can study it locally. There's a lot to say about it, also locally. But what I focus on today is the global theory. And I'll try to give you an idea, just very sketchy now, give you an idea of why logarithmic geometry is the right tool to deal with those kind of singularities. And the reason is, so maybe one little thing I say, I also typically have an extra deformation parameter t, which I put over here, times t to the k. But the point is, so the theory is relative over the affine line, which is given by t. So it's a deformation situation. We deform the singularity into even worse one when t goes to 0. That's even worse then. But the point, why is logarithmic geometry the right tool to deal with those kind of singularities? Roughly speaking, you can say, so you probably have all seen the definition of what a log structure is. I'll just repeat it here. So if you have a variety x, or can be any scheme, then logarithmic geometry is looking at an extension of so what this is it's an exact sequence of monoid sheaves. Monoid here means it's a semigroup with unit. That's why mono is unit. And it's commutative. So what you might think of here, you have, this is a sheaf where the stalks might be something like n to the k. This is a typical monoid. So I have on the right-hand side a sheaf of monoids with stalks of finitely generate monoids like n to the k. That's a monoid with addition. And over here, I have the sheaf of invertible functions on the scheme, which is the monoid under multiplication. And so the log structure is the thing in the middle. It's an extension of a very easy monoid like n to the k, or more generally, monoids that you know from toric geometry you can put here. But in the sheafy version, so this is, I'm talking about stalks now. But anyhow, the stalks are like this. And you extend it with the structure sheaf. Okay? So then that's not all it is. There's also a map from this thing in the middle into the structure sheaf. And the map has the property that if you look at the inverse image of the invertibles here, they identify with the invertibles over here. Okay. So that's a very quick introduction to log structures. But the point I'm trying to make with illustrating this is that you can think of log geometry as an extension of, this is, you can say, toric geometry, or some people also call it tropical. And this, you can, over here, we're in the realm of algebraic geometry. So logarithmic geometry has these two flavors. It has a flavor of toric geometry and tropical geometry, but it's also very classical algebraic geometry. And it's really the combination of two. So there is some part of it which is combinatorial. This thing is discrete, has a combinatorial flavor. And there's a part that's really algebraic. And both these things make up a log structure, and you have to consider both of that. So how does it match with what I talked about before? Well, roughly speaking, these monoids are what govern my left-hand side over here in the singularity. So I generalize away from this. As I said, the left-hand side generally is a toric singularity. So it's given by some monoid, and that's what this M bar is. So that's governing, telling you what's over here. And then what's on the right-hand side? Well, that's roughly where you have a section of the invertible functions, but in fact, it's allowed to vanish. So that's where F vanishes. F is, strictly speaking, supposed to be a section here, but it does vanish somewhere, so then it's no longer a section here. And that's when the log structure receives singularities. So the singularity of the usual, it's an ordinary singularity, but you can also, once you put it in the language of log structures, it also becomes a singularity of the log structure. Okay? It might seem to make it worse, but actually that helps to deal with the situation and to globalize it. It's just very sketchy, but that's just, in a nutshell, what I'm doing. So I'll now switch gears and go in a different direction. I'll give you motivation. So it's completely going away from this now, but we'll come back to that in the end. So I'd like to give you motivation of why I look at those kind of situations. It's a very big picture situation. Do that. So the motivation is two types. One type of motivation is mirror symmetry. It's something that I'm very interested in. And there's a lot to say about it. It's been going in all kinds of directions in mathematics. It's originally from physics. As you know, I don't need to tell you much. You've seen many conferences on that topic. So I'll focus on the particular construction, the Gauss-Seibert construction. And I'll put it in a nutshell. So again, you could spend lecture series about that. But I'll put it in just 3 points. What is the Gauss-Seibert construction? And it's a three-step process, how you do mirror symmetry for a space. So you start with X. Pick your favorite Calabi-Yau manifold or Fano. That's where the program works best. So that's a manifold, say X is either Calabi-Yau or Fano, and put this in a degenerative family and pick a flat degeneration. The family over a disk. So that means that this original variety appears here as a fiber, as a non-zero fiber somewhere. It's there. So you extend that to a family. Maybe that doesn't work for all of those Fanos and Calabis. But if you can do that, then you're in good shape to run the steps of this program. So you put it in degenerating families so that the central fiber, call that map pi. So this is the inverse image of the origin. That this one is a union of toric varieties. And these toric varieties are supposed to meet each other. So it's a reducible union of toric varieties. And they meet each other in toric boundary strata. Meeting. Okay, so what you can think of typically is the quintic family. I put this as an example up here in the corner. E.g., you can take your quintic in P4. That will, let's go by x0 to the 5 you take the Fermat quintic, and then you put a family parameter, put a t here, and then put this x0 times x4, okay? So that's exactly doing this. The quintic is given by, in homogeneous coordinates, by this x0 to x4. It's the Fermat quintic in P4. And you put a parameter t here, so that when t goes to 0, you end up with that monomial, and that's just a union of coordinate hyperplanes, okay? So a coordinate hyperplane in P4 is a P3, and you have then 5 P3s, and they meet each other in P2s, so that's fitting the setup of this construction. That's a typical example. But there are many more examples. Okay, I need to use this thing. Oh. Well, it's much better than what we're going to have in Hamburg. Hamburg is very difficult to operate. But I have to get that one up. No? Maybe I should say that. Ah, here we go. Okay, so I promised you this 3-step process. I've done the first step. And then there are 2 more steps. The next step is that you apply a combinatorial duality to the central fiber in this degeneration. To x0 to obtain some dual space. Okay? So this duality has many names. Polar duality, Legendre transform. You can say you go from the intersection complex to the dual intersection complex, but it's a very trivial, more or less trivial thing. There's not much depth in it. Because what we did is we took the variety and we degenerated in a way where it became rather combinatorial. If the union of hyperplanes in P4 there's not much geometry to it. And then you apply this very stupid duality. But still it can be more difficult because if somehow this duality should of course capture the geometry that we lost in the process of degenerating, and then depending on how much decoration you want to add to the duality, it becomes more difficult. But roughly that's what you do. And then the next step is to reverse the first step. So now you want to produce the smoothing of the variety you end up with in the duality. Produce a smoothing of x0 check to obtain the mirror dual. And in fact, so what you see, you don't just get one mirror, you get a family of things. You can say x check over a disk. But so you should think the general member of the smoothing of this, so it means that the central fiber is isomorphic to the space you start with, but you have deformed in a flat family, and the nearby fibers are smooth. If you're able to do this, then the nearby fibers would be what you consider your mirror dual to the original space. Okay? It's roughly a geometric construction of mirror symmetry. And a lot of evidence for this work being the right thing to do. Okay, so the remark is, first, of course, each step can be a challenge. The evidence for why this is a good construction, that all steps have been verified to work for Calabi-Yau complete intersections. Complete intersections in toric varieties. So those that invented the combinatorics of this was Barterev and Borisov. And in fact, they also provided a duality that didn't need to do the degeneration. they had their own way to do it. It's very closely related to this combinatorial duality. They use just polytopes and polar duality for polytopes and the Neff partitions and so on. But you can phrase that construction that they provide also in this degeneration framework, and just works perfectly. And the advantage of this degeneration framework is that you don't need an ambient space. So here, by construction, you start with an ambient space. The Calabi-Yau complete section lives in a Fano, but to some sense that's unnatural for the Calabi-Yau itself. You can also do this construction for not being an ambient space. Then the next thing where it works nicely, all steps work when x, so in some sense you input the first step already when x is a normal crossing degeneration. Crossing. So that means dsym is stable. Degeneration of a Calabi-Yau or Fano. So this is more recent, and it goes under the name intrinsic mirror symmetry. And it was proved by Gross and Siebert. Okay. Then what's also nice about this construction, oh, and I'm not allowed to use that one. Oh, that's the big one. Let's just stay there.
I have a question. So when I was reading in Gross Siebert program, there were some Lagrangian toroid vibrations around. Can you briefly mention how they fit or in they fit?
Yes. So, right. An important part of mirror symmetry is the T-duality. So there's a paper called Mirror Symmetry is T-duality by Manjaro and Zaslow. And one advantage of this three-step process, for instance, over the Bardorov-Borisov approach, is that it has a natural inclusion for the T-duality. And let me sketch that quickly. So when you have your original variety, then it's in a flat family, and that allows you to write down a retraction map. There are many different versions for that. Clement studied that. You can use symplectic structures to do that. But choose your favorite retraction map to the center fiber. And then, because the center fiber is a union of toric varieties, you can map that with the moment maps to a union of polytopes. Just sketch that. So each component of the center fiber is a toric variety. If they're projective, they're given by a polytope. You use the moment maps. You can glue them, the moment maps, and then get a map to a space that has half the real dimension. And the composition of those, this composition here, this is the torus vibration. Okay. And the main point, if you run the same composition here for the dual situation, we have that very similarly. Then, in fact, here, in some sense, you have dual polytopes. And the point is here that you have a homeomorphism, homomorphic. And this is a T-dual torus vibration. Okay? So it's dual to the original one. That's why this is very compatible with T-duality. You naturally get those dual torus vibrations using this homeomorphism. Okay? So here, B is something like the intersection complex of the original degeneration. And then B check would be the dual intersection complex of the original degeneration. And the intersection complex of the dual degeneration. So these are homomorphic, and then under that homomorphism, you get these dual torus vibrations. And you can enhance that picture in all kinds of ways. For instance, that should really be a Lagrangian torus vibration. And I'm working on that myself, so we can prove it, for instance, in the situation for Bhattacharya-Calabi-Yau's. I believe in all dimensions, it's something I'm working on, that you have these dual vibrations, torus vibration as Lagrangian torus vibrations. Okay, that's maybe the T-duality point of view. Just add it. And another point I wanted to mention, maybe it's of interest to you, the construction generalizes the ax duality of cluster varieties. Okay, maybe you know cluster varieties. There's a cluster A variety, cluster X variety. They are given by dual tori, or basically you dualize your C torus, and then you get the dual cluster variety. And this construction is totally compatible with that, sort of reproducing it for cluster varieties if you input a cluster variety into the construction. Okay. So that's a bit of advertisement for this degeneration approach to mirror symmetry. That was the first part of my motivation. Part A, now I come to part B. That's what my current project is motivated by. So it's the idea to use mirror symmetry, or roughly this construction and what's around it, to classify Fano manifolds. Okay, and that's not my idea. It's been put forward by many people. Duku is one of them. But the paper that's been written on this is by Coates, Corti, Galkin, Golishev, and Kapstruk. That's a little hard to spell and write, but I'll do my best. Okay, so there's a paper which says mirror symmetry and Fano varieties, or Fano varieties and mirror symmetry, something like that. And they spell out how they seek to use the mirror symmetry construction to classify Fano manifolds. If you're not so familiar with that, let me quickly give you the broad keystrokes about Fano manifolds, what the state knowledge is about them at the moment. Let me get this up here. So some fun facts about Fano manifolds. In dimension 2, these are just little Pezzo surfaces. That was his theorem by de Pezzo. There are 105 families of smooth Fano threefolds. Okay, so that's known, and 98 of them have very ample anticanonical divisor. So Fano is defined by having an ample anticanonical and sometimes very ample. In most cases, in fact, here it is. So that much is known. If you look into what these are, it's a bit of a zoo. So you find one here. P3 is one of them, but many more. You don't see a coherent scheme at the moment. And what I'm providing, hopefully, is a coherent scheme to produce them all in one go, roughly speaking. And that's a bit of a motivation, but also to go beyond that in high dimensions. Let me try and get this up. No, that's the wrong one. This one. Okay, let me leave that here. I'll go back to it. Okay, so then there's a recent result, maybe which you've seen. I like to mention it because it's nice in this context. That, you know, like for Calabi-Yau manifolds, it's unknown how many there are, how many families there are in dimension 3. It's an open problem. But for Fanos, this has recently been solved, to some degree at least, that there are finitely many. So the boundedness of Fanos manifolds in all dimensions was proved by Birkar. And that's very recent. It was published in Annals this year. So you know that there will be finitely many families in any dimension, but what's open is how many there are. So it's unknown how many and which, of course, families in dimension 4. And there's also stuff unknown in dimension 3. For instance, if you generalize away from being smooth, if you go to a Hugh-Gorenstein Fano, then it's also unknown how many you have of that. Okay, so the rough guess in which price range that's happening is something like 60,000, I think. You know, but nobody knows for sure, and maybe this one around 40,000. But then, you know, it's just nobody knows that really. But people working on it is Alessio Corti, for instance. He has a lot of data knowledge on that question. So that's something I'm interested in. And let me quickly sketch how you can use possibly the construction of steps 1, 2, 3, which produces the mirror symmetry, to classify Fano manifolds, so going from motivation A to motivation B. And this works as follows. So you classify the mirror dual of a Fano manifold. The mirror dual X of a Fano X check is a Lerner-Ginzburg model so that means it's not just a variety, but it's an affine variety together with a regular function. Say we work with the complex numbers, so this is a non-constant regular function. It's a very different thing. It's more local, and X is affine. So the Fano is projective, but its mirror dual is an affine variety. It's a bit weird maybe, but that's what it is. And it comes together with this function. So that's a very different object. And the idea of how you want to use mirror symmetry to classify Fano manifolds is you want to classify those functions. Okay? And that might be an easier problem. So the idea is, so classify W instead of the Fano X, okay? So you'd rather have this, well, I should say a check here, I'm sorry for that. Fano is check, that's right, instead of X check. So rather classify this Lerner-Ginzburg model than the Fano, and if you know what Lerner-Ginzburg models you have, you can apply the construction and get the Fanos. That's a rough idea. Okay, that's my motivation. Any questions, you just shoot them in.
So this function W, does it somehow come out of this 3 steps thing which you explained before?
Good point. So the idea, also using my notation, is that X is supposed to be the input. So in the 3 steps, I start with X, and then I get X checked from X. But you write this function is closely connected to X check. So if you have X check, you can write down W easily. If you don't have W, then X is just mostly a combinatorial space. It doesn't know W. But if you have a way, somehow, from a different means, to have an understanding of what W's are permitted, then you can use this X and W and plug it into the construction. And then you can get out an X check. Okay? I didn't explain that, how that works. You know, there's an adaptation to the construction where you put this W and then you get that out. But it can be done. But the idea really is that the underlying space X is very boring. Oftentimes just an algebraic torus. The function is really the interesting thing. But if you have some means to classify those W's, for instance by differential equations or something like that, then you will be able to plug in the construction and then get out a Fano out of that from the construction. Thank you for the clarification. Okay. They don't go simultaneously. Okay. All right. So I will spend most of my focus on step 3, which is about smoothing. Okay, so I assume for the purpose of applying this to Fano manifolds, I'm not looking into the process where you would come up with these starting data W and so on, but I assume that you have a space X0 check, which is glued from toric varieties, and you want to smooth it. So it's a step 3 that I'll focus on. But what this W gives you as an input is a log structure on X check. Okay, so the underlying space is often boring if you just know the underlying space X0 check. There's not much in it, it's combinatorial. But the interesting information is the log structure. So in the sense of this extension, this is sort of combinatorial on the right-hand side. Once you have the functions for this f up there, then that's what W is. Okay, the Logarithm potential gives you this f in the singularity up there. So I'm sorry for not explaining you that part, but for instance, people like Alessio Corti would be much better in doing so, but some of that is also not even completely understood yet. But what is understood is what kind of log singularities you come up with. So you classify what this W can be, then there's a procedure how you turn this W into singularities or a bunch of singularities with those F's there. And then you want a way to smooth that. And I'm talking about the smoothing of that. And for that purpose, I need to look a bit more into what that singularity really is. What is the definition for the general sort of thing of that? And let me do that. Definition. A toroidal crossing singularity is one which is, so it's a singularity, which is état locally equivalent to the following form. You take the spectrum of a monoid ring and you mod out a monomial. Okay, let me explain what that is. So here, this is an ideal, principal ideal generated by a single element. Here P, P is in some z to the n plus 1, is a toric monoid. So for that to really be, for instance, you can think of P being, as I said before, n to the r to n plus 1 in this case. Could just be the non-negative elements in z to the n plus 1. That will be giving something interesting. That will give a normal crossing singularity. Or it can be any toric monoids. Generally, P is the intersection of a cone. In the usual toric language, it's a dual cone, which you then intersect with a lattice. So you take a polyhedral cone and intersect it with a lattice. You get a monoid, and then you can take the monoid algebra. Okay? So the CP is the set of all finite sums with coefficients P, ZP. AP is a complex number, and P is in P, and the sum is finite. Okay, that's maybe squeezy here. Hope you can read it. So it's just the usual way to define a group algebra. You can also define it as a monoid algebra. You take these formal sums, coefficients are in your field, and then there's some elements here which I write z to the p. They're like characters, and you have them for all the elements in the monoid. and then multiplication, the monoid operation becomes multiplication in this ring. Okay. And what is this z to the rho? So rho in P is an element such that, sorry, I need to write over here, such that the divisor of this element, it's a principal divisor, is the reduced union of toric prime divisors in this affine toric variety. So when you form this monoid algebra, that's an affine toric variety, and it has a toric boundary, and you want this principal divisor to give you a toric boundary. This is another way to say it gives you a toric boundary. Div of z rho equals toric boundary. So such an element doesn't exist in general. This exists, rho exists, if and only if the variety is Gorenstein, or the ring is Gorenstein, okay? Because this is also called a Gorenstein parameter, is a Gorenstein parameter.
Those monoids are separated?
Yeah. Yeah, automatically. When you take a polyhedral cone, so it's a cone in a vector space, good point, right? You take a cone in a vector space and you intersect with that, it's automatically calibrated.
But you only consider?
I'm only considering those, yeah, only those kind of things. Well, the definition of toric monoid is this one. Yeah. There's also an intrinsic definition, but that's the easiest way to say it. Okay. No, that's the wrong one. That's the one. Get down. I need the top one. Yeah. So you see that this is a generalization of a normal crossing singularity. If you put in, for this monoid P, if you put in the natural numbers to the n plus 1, as I said as an example, n to the n plus 1, then you can choose for rho the element that's 1, 1, 1, 1, 1, so it's 1 in every entry. And what you end up with then is exactly a normal crossing singularity. So these toroidal crossing singularities are a generalization of normal crossing singularities. And you may ask, why is normal crossing enough? Because for many purposes, if you listen to talks or anything, people often talk about normal crossing. I mean, the resolution of singularities, of course, gives you that normal crossing is enough if you permit yourself this resolution. But if you think about it, if you want to apply combinatorial duality to some normal crossing space, then the dual will typically not be normal crossing. I mean, normal crossing means that you have some simpliciality, but under this duality, it's not going to be preserved. And that's why you're forced to go more general to toroidal crossing if you want this combinatorial duality to work out. Okay. Right. So the next step, because I said I want to go global, is to explain how you generalize or to sheafify this construction. So what I gave you above is a local description, and there's an easy globalization by sheafifying it. Let me explain that to you. So before I do that, let me give you equivalent descriptions of the data here. Remark. The data P and rho, okay, So given that, it's equivalent to the following. To a complete fan in Rn. So that's maybe a bit surprising. So what is that? So you have your Rn, it's a plane, and then you have it decomposed into a union of cones. So there's some object from toric geometry, complete fan, so you decompose your Rn into cones, together with a strictly convex function phi, which goes from Rn to R, that inducing the fan. Okay? So that means that you have, on top of this Rn, this is Rn here with a fan in it, you have a function, and the function is linear on each of the cones, and it's not linear where two cones meet in the faces between the cones. So it's bending exactly there, and it's strictly convex. So yeah, it's a strictly convex function where it's nonlinear exactly in the strata of this fan. So that's maybe hard to digest. Let's do an example here. So for instance, if I take, oh yeah, maybe before I do the example, sorry for that. Once you have that description, let me add one extra step. This is maybe remark part A. Remark part B is hence the data P rho is also equivalent. So if you know a bit of toric geometry, then you know that a fan with a strictly convex function is the same as a projective toric variety together with a choice of ample class. Okay? So it's equivalent, in fact, you know, with a divisor, toric ample divisor, is equivalent to a projective toric variety with ample toric divisor. Okay. So let me give you an example how that connects to this toroidal singularity. It's maybe a bit funny, but it's the local version of the duality that I gave you in point 2. Remember the construction and motivation A? I had these two steps, and the second step was a combinatorial duality. This is a local version of it. So if you have this toroidal singularity, you're able to make a dual of that, and the dual of that is a projective toric variety. And here goes for P1 how this works. So if I start with the projective one, I can tell you what the toric singularity is associated to it. If this is the dual thing I end up with from this point B, so what will be the associated toric singularity? It's easy to say when you go this way. So you do the fan for P1 just looks like that. It's a fan on R. And then K is supposed to be non-negative, and it gives you exactly the bending of a piecewise linear function here. So, you know, you can think of taking this linear function, which is 0 here, and then it has slope minus K here. Okay? So that yellow thing will be a graph of a piecewise linear function on R, and it's linear on each of the two cones. So each of the rays is linear, and it bends by slope change K at the origin. Okay? So this is the toric picture for P1 with this ample line model. Okay? Probably know, if you know toric geometry, you've seen this. And the point is, how do you get from that a toroidal singularity? Well, now, once you have that, you can take the convex hull of this cone, so of the graph. So here's this graph. You take the convex hull of the graph. You put your, what you can call sigma dual, is the convex hull of the graph of phi. Okay? And then you define your monoid P to be this convex hull intersected with now z to the n plus 1. In our case, that's z2. Okay, so you have here lattice points, and you intersect with that. Oh, I'm making funny noises. So in my example here with those lattice points, the slope k would just be minus 1 would be the slope, k would be 1. So intersect with that, and then the blue points, all the blue points that lie in this yellow cone, they will give you the monoid. And which element do you choose for rho? Remember that this is element rho, the Gorenstein parameter, that you also need to have for toric singularity. For rho is simply the element that's 0, 0, 0, 1. In our case, in this example, let me just say. So it has all entries 0 in the bottom Rn, and then it has 1 in the last entry. So in this picture, it's really this element here. It's generating the vertical direction, the new R, which you have from making a graph. Okay, so this is rho. And it's interesting that this is a bit of a lemma, that this is in fact equivalent. So if you have this, you start a projective toric variety with this toric variety, you get toroidal singularity, and vice versa. Okay? Up to adding a linear function to that. If you add to this piece of linear function, if you add a linear function, then the singularity doesn't change. Okay, so that means just you replace the toric divisor by a linearly equivalent divisor. All right. So here's here a nutshell this combinatorial duality in point 2 that I gave you in local version. And you should think of that when I have a toric generation, the generation into union of toric varieties, each toric variety gives me locally a toroidal singularity, and you can glue them, and then you get the dual space. And vice versa, if you have a space that has these toroidal singularities, you get a component for each singularity, you get a projective toric variety, you glue them, and get the dual space. So you see roughly how this combinatorial duality works. But of course, life is more difficult than just that combinatorics. I'll come to that next. Unless you have questions. Maybe use this one. Okay. So once you understand this local picture of what a toroidal crossing singularity is, there's an easy way to sheetify it. You know, I guess you could come up, once I tell you you should sheetify, you probably come up with the definition yourself. But I can also give it to you. So the globalization version of this is the following. This is from Siebert. Schröder first came up with this as a generalization of normal crossing, a toroidal crossing variety so that's the kind of variety that we use for x and x0 and x0 check in the construction. But I call it x now. Or maybe I use the 0 here just to make the connection clear to the previous point. So that's a triple where, well, let's say, is a variety x0 is just a variety, but it has some features with a sheaf of monoids. Monoids P and a global section. Gamma is a global section of this sheaf on the variety, such that locally it's given by this data, such that at every point, x bar and x eta locally, x point is the toroidal crossing singularity given by p x bar rho x bar. So you have this data globally. P is a sheaf, rho is a section in it. You can look at it at every point, x bar, and then the space is supposed to be given by that type of singularity at the point. Okay? And that's not quite enough, but you also need some coherence. But that's not hard to understand, because once you have a toroidal crossing singularity, every other point in the neighborhood of that singularity is also toroidal crossing singularity, not necessarily for the same monoid, but for localization of the monoid. And coherence just means that this works with neighborhoods. So if you have a point which gives you this model, then it's also the same model for the nearby points, and the nearby points don't have different models than what you expect them to have. That's a coherence. Okay? So that's a stupid way, it's not any depth in it, to just generalize this local picture by a sheafified version. Okay. So now we need to talk about how we get to, oh, where are you going? Stay here. How we get to the F part. On purpose, I left this original thing that I wrote there on the board. So all I talked about now was the left-hand side, where I just wrote xy up there, xy. But you replace the right-hand side with something else. The t is the rho, okay? T is the rho parameter. But the interesting thing I haven't talked about is this f. Okay. So the theorem around this story is that if your toroidal crossing space x0 carries and carries of a sheaf which is called LS, then x0 is smoothable. Felten and Philip, and appeared in the forum of Pi, from Mathematics Pi this year, which you can naturally put on the space. It takes as input the sheaf P, this sheaf of monoids, and the global section, and then you can cook up a sheaf which controls the left-hand side monoid sheaf M bar there, is the sheaf P, and they still have to put something for the left-hand side. And what you can put there is controlled by the sheaf LS. It's a sheaf of log structures. Okay? And I need to tell you a little bit about this LS's. So LS, if then this sheaf LS is the same as canonically isomorphic to the T1 sheaf. Okay, so it's not so crazy. It's a natural sheaf. To be honest, as it comes to you as a sheaf of sets, so here it becomes a coherent sheaf this way, it's been a direct sum of line bundles on the singular set of your variety. Okay? More generally, this LS x0 is a metric sheaf of the push forward of the what do we say? The direct sum of n c, where c are components of x sing, and these are line bundles. Okay, so it's not so crazy. There's a line bundle on each component of the single locus of your space, and the sheaf that classifies log structures is a subsheaf of that, given by some understandable condition. And so there's a nice way to smooth this. And yeah, I'm running out of time. I'll let you ask questions. So, you poke me if you want to hear anything else, then you say it. I'm done with my part.
So, thank you for a nice talk. Are there questions?
What simple section?
Again?
What simple?
What simple section? Simple here is just transverse, that the zero set of the section. So because it's in a set of line models, it may vanish somewhere. And where it vanishes gives you sub-variety. Yeah? So the zero locus of the section is supposed to be transverse to the strata. The variety is given by all kinds of strata. And if the section is transverse to the strata, then that's a simple section. Okay? And the main point, which I haven't been able to do this today, but is that you want this also to work for more general sections. And that's what I'm currently working on with Felten, Philip, Petracci, and Corti. So we make this theorem also work for more general sections. Say again?
So what do you mean by transverse? Just in terms of dimension?
Smooth intersection. So for instance, up there, so if you look at the equation up here, this f, the equation f there, that's the section of this LS. Okay? So exactly, if you look at the underlying space, if you send t to 0, then you just have two smooth pieces meeting in some single locus.
But I thought that you allow arbitrary toric singularity, not just...
Yes, on the left-hand side. Right. So you have arbitrary toric singularities, and they take that toric singularity with product with some smooth space. Because the toric singularities give you how the components meet each other. That's controlled by a toroidal crossing singularity. But then on the locus where they meet, you still have this section f that may vanish somewhere. And then this f governs sort of extra singularity, if you like. Okay, so most of my talk I spent about talk on the left-hand side. But then you have this f, and if this f is a smooth, regular hypersurface, then I'm saying basically I can smooth it. That's roughly the statement. The section is simple if this f is a smooth hypersurface. And I want to generalize away from that.
Are there any other questions? No? So let us thank the speaker again.